So for number 14, we're trying to figure out the KEQ for this voltaic cell here. And so we have a redox reaction, we can get some cell potential, and then eventually we can relate the standard cell potential to KEQ. We know that E standard is going to be equal to 0.0592 divided by n times the log of KEQ. And so here I've split the reaction into its two half reactions. So we can see that the copper, so I've dissociated the nitrate away as a spectator. So we have copper 2+, gaining 2 electrons to become copper solid. And we have zinc being oxidized to become zinc 2+, and giving off 2 electrons. And so if you go on to the data sheet, you can find these reductions. And so, or the potentials from the reduction potentials. So for copper, it's positive 0.337 volts. And when I find the zinc reduction potential on the table, it's negative 0.763 volts. But here we have the oxidation. We're doing the reverse reaction. We're oxidizing the metal instead of reducing the ion. And so I'm going to change the sign, and it's going to be positive 0.763 volts. And so then we can add these together to get the standard cell potential, which is just 1.1 volts, and that's positive. And then we can get our overall reaction also. So our electrons are the same number, so they'll cancel when we add these two reactions together. And we'll get our overall reaction where copper ions that are aqueous will react with the solid zinc to form aqueous zinc ions and solid copper. Okay, so we can go ahead and say that 1.1 volts is equal to 0.0592 divided by n. So n is our number of electrons that were transferred. And so for this reaction, it's going to be 2 times the log of KEQ. So then we can solve and see that 37.16 is equal to the log of KEQ. And then we can do 10 to the power of both sides to solve for KEQ. And we get that it's a huge KEQ. It's equal to 1.45 times 10 to the positive 37, which corresponds to answer choice B. In number 15, they give us this reaction with solid AgBr and cyanide becoming the complex and kicking out the bromide. So they've given us a Ksp and a Kf. And so what I've done here is just written out those two reactions. We know Ksp is always the solid breaking up into ions, whereas Kf are the ions coming together to form that complex. And so when we write these out, then we can start to see how, as is, Ag+, which isn't in our above reaction, cancels out. And then we're left with that overall equation. And so since we've just added these two equations together to get our overall one, our KEQ will just be equal to Ksp times Kf. So we'll just do 5 times 10 to the negative 13 times 5.3 times 10 to the 18th, and we get a KEQ equal to 2.65 times 10 to the power of 6, which is answer choice E. Okay, so our good friend Rick wants to make a platinum coated collar, and he's going to do the electrolysis to plate that platinum out. And so he wants to figure out how much platinum he could plate out if he used 1 amp of current for 1 hour. Okay, so whenever I see an amp, I automatically change that into coulomb per second. So to start, I'm going to begin with the number that's just a constant, just a number, and that's my 1 hour. And then I'm going to convert that to seconds by saying there's 3,600 seconds in an hour. And then I want to cancel out seconds, and I know that also I have 1 coulomb per second that's being put in. So this is where I can use the current. And then now I have coulombs, and I can use Faraday's constant, which I've written above, and say that there's 96485 coulombs of charge in a mole of electrons. So now I have to think, well, I've miswritten my equation, so let's change the equation and fix that. So here we have platinum chloride, Cl2. So what we actually have to start is platinum 2+. So we can take our platinum 2+, and to plate it out as the solid neutral platinum, we'll have to put in 2 electrons. So for every 1 mole of platinum solid that we would get out, we would have had to put in 2 moles of electrons. And then we can say that 1 mole of platinum weighs 195.08 grams according to the periodic table. So now we've canceled hours, canceled seconds, canceled coulombs, canceled electrons, canceled moles of platinum, and are left with grams of platinum. And that number ends up being 3.64 grams of platinum. So Rick might need to either use a higher current or let the reaction go longer if he wants to coat his whole collar. So number 17, we have the Haber process. And they give us the rate of consumption of the H2. And from that, they want us to figure out the rate of production of the ammonia. And whenever we're converting between the rates of two things is when we have to use the coefficients. And so here I've written, so since it's leaving, I have this negative sign for the H2. But we have 1/3, because of that 3, times the rate for hydrogen to be equal to 1/2, because of that 2, times the rate of ammonia appearance. And so I'm going to say 1/3 times my 5.2 molar per minute is equal to 1/2 times the rate that I'm interested in, so I'm just going to call that x. And because rates are always positive, I dropped the negative sign. And I know that the H2 is going away because it's a reactant, and that ammonia is increasing in concentration because it's a product. And so when I solve for x, which is really that rate of ammonia appearance, you get 3.466 molarity per minute for its rate, which is answer choice E. So here, number 18, they give us a reaction. We have a graph, and they ask how long it will take for the sodium iodide concentration to drop from 1 molar to 0.25 molar. So when I look at the graph, I look at these x and y axes, and I see I have time and I have change in sodium iodide concentration, but it's 1 over that value. And so this tells me that I have a second order reaction. It's a reaction of second order with regard to sodium iodide concentration. And so I'm going to use the second order integrated rate law to solve this. So that will be 1 over concentration of, yes, let's go ahead and say sodium iodide, time at whatever later time, divided by its initial concentration, plus Kt. And they've given me those concentrations here. So I have my initial sodium iodide concentration of 1 molar and my later concentration of 0.25 molar. And we're trying to figure out how long it'll take for this change to happen. I'm solving for T, and I'm also going to need to figure out K. I'm going to get K from the slope of the graph. Because if we think about 1 over concentration changing as the y-axis times the x, then plus K will be my slope. So I can go ahead and plug the numbers in, and I'll have 1 over 0.25 molar equal to 1 over 1 molar plus the K, 0.0002 inverse molar inverse seconds times T that we can solve for. And when I plug this in and solve for T, I get 15,000 seconds. So this would correspond to answer choice B. So now we're going to use that graph. Well, we'll think about, for that substitution, what we'd have to do to figure out the activation energy. And so when I think about determining activation energy, I think about the Arrhenius equation, which is K being equal to the Arrhenius factor A times e to the negative EA over RT. And sometimes you'll see this written as the natural log version, where we have the natural log of K equal to the natural log of A minus EA over RT. And so these are the equations that kind of connect rate and activation energy and temperature all together. And so if we look back at the previous slide, you can see nowhere in our equation that we used was activation energy present. And so we can't get activation energy from this alone. we would need a plot with activation energy or temperature and rate. So A and B are going to not be the answer. C says a plot of ln K versus 1 over temperature is needed, which gives a straight line whose slope is negative EA over R. Okay, so answer choice C seems promising because we could make a graph where this is the Y, this is B. We can make 1 over T the X, and so the slope then would be negative EA over R. R is just a constant, so then we could figure out activation energy. And so answer choice B says if we just plot K and temperature straight out, and that wouldn't give us a plot. That would give us an interesting exponential plot, but not what we're going for. And then E says a plot of the natural log of that concentration versus time. And that would tell us about how a first order reaction would change. But we know from the last problem that it's second order, and this just doesn't make sense. So C would be the correct answer.